Welcome to Lecture 16. This is on degenerate Rayleigh-Schrödinger perturbation theory. This is what happens when we have multiple energy levels that have the same energy eigenvalue as the state that we're trying to perturb. So again, our Hamiltonian is separated into the two terms, the H0 plus V. We now have a set of states that are indexed by a K and an n sub k. N sub k will run from 1 all the way up to d of k, where d of k is the degeneracy of the level k. So in the non-degenerate perturbation theory, every nk was equal to 1. In degenerate perturbation theory, we have at least one state that has a d of k that is larger than 1, and we're looking for the perturbation of that state when we're working on the degenerate perturbation theory calculations. The eigenvalue eigenvector relation is still the same form. H0 acting on the ket k comma nk sub 0 is equal to E0 k comma nk. That should be a sub 0 at the end of that. Now we assume every one of these states are orthogonal to each other as we index through n sub k. And what you really should keep in mind is we have a d-dimensional vector space here. And there's some basis for that d-dimensional vector space. We're going to use this initial set of k comma nk sub zeros as that basis for the vector space. And then the eigenvalue equation that we want to solve is H0 plus V acting on the state k comma nk without a 0 is equal to E k comma nk times that ket k comma nk. Now, the perturbation V might totally lift the degeneracy, it might partially lift the degeneracy, or it might not lift it at all. And so you can already see with degenerate perturbation theory, there's lots of different things that can go on. We're going to again follow the exact same Rayleigh-Schrödinger strategy. We're going to separate out, moving the H0 to one side and moving the delta EK comma NK onto the opposite side. So we'll have EK0 minus H0 acting on the state K comma nk is equal to v hat minus delta ek comma nk acting on the ket k comma nk. Now, as before, we need to protect the inversion of this equation with projection operators because we can't just divide by the operator ek0 minus h0 because that operator vanishes inside this entire degenerate subspace. So we're going to define the projection operator pk, which now has a number of terms. It'll be a sum nk equals 0 to d of k of the ket bra product k comma nk 0, 0, k comma nk, and that projects us onto the ek0 subspace. You can easily check that it's a projection operator by simply calculating the square of the operator, because the overlap of a k nk with a k nk prime is going to give me a delta nk prime. Because all of those states are orthonormal, you get back the original projection operator pk. So pk squared is equal to pk. And then if we define qk as 1 minus pk, that's also a projection operator because it projects perpendicular to that degenerate subspace. And it's the exact same proof as what we did before when we proved that qk was a projection operator in the non-degenerate case. Now, we have to note further that the pk and the qk each commute with the Hamiltonian. Again, the proof is very simple, same thing as what we had done the last time, because the pk and the qk are expressed in terms of eigenfunctions of the Hamiltonian H0. When we evaluate those commutators, we get the same number subtracted from each other, and so that's equal to 0. Now we're going to do the same strategy. We're going to take that Schrödinger equation, multiply it by qk. The qk can go through the ek0 minus h0 on the left-hand side. It cannot on the right-hand side, so it has to sit there. We're going to call the projection of qk onto k comma nk. We're going to call that k comma nk perpendicular. It's a piece of the ket vector that we are trying to search for, but the parallel piece now has potentially a number of terms in it given as a linear combination of the degenerate eigenstates. So then if we can now invert that operator and get the k comma nk perpendicular is equal to qk over ek0 minus h0 times v hat minus delta ek comma nk acting on the k comma nk. We now are going to write the k comma nk as k comma nk parallel plus k comma nk perpendicular. We get that by operating the pk plus the qk onto the state. The parallel piece we're going to leave, and we're going to take the term that is multiplying the perpendicular piece with the qk. We're going to bring it to the other side, and then we're going to take the inverse operator of that. So we're going to finally end up with k comma nk is equal to 1 minus qk over ek0 minus h0 v hat minus delta ek comma nk whole thing inverse times k comma nk parallel. Okay, and again, very, very similar to what we did with the non-degenerate case, except for the fact that the projection operator is more complicated, and we now have to figure out this parallel component because everything for the ket k comma nk is built off what that parallel component is. Right? In non-degenerate perturbation theory, that state was known because there was only one state, so it had to be the state k comma nk parallel. But in degenerate perturbation theory, we actually don't know what it is, because if you look at operating pk onto the state k, I can write that as k 0, 0k, comma, the bracket sandwich 0k, comma k, which we set equal to 1, and that's just equal to k0. That's the non-degenerate case. In degenerate perturbation theory, when we operate that pk on our state, we're going to get a sum of different terms. I have a k comma nk prime. Nk prime is summed from 1 to d of k. And I have the set of numbers, this bracket sandwich, 0, k, comma, nk prime with k, comma, nk. That's an inner product, and those are just numbers, but we don't know what those numbers are. So I can't tell you what that k, comma, nk parallel is. So we're going to have to find an equation that will allow us to determine what those numbers are. And that's called finding the parallel component in the degenerate subspace. So I want you to remember that because it sounds kind of confusing, and students often have situations where they forget exactly what it is we're doing with that. And I just want you to remember we're looking for a specific vector in that degenerate subspace. It can be expanded in terms of the basis vectors of that degenerate subspace with a set of numbers, but we don't know what those numbers are a priori, so we're going to have to figure out what those numbers are, and we're going to have to find an equation that will allow us to figure out what those numbers are. All right? Now, let's recall again that the perpendicular component is given by qk multiplying the full state k comma nk, which we broke up into the parallel component and the perpendicular component. If I hit it with a qk, I'm only going to pick up the perpendicular component, so we'll get a qk 1 minus qk over ek0 minus h0 v minus delta ek comma nk whole thing inverse times the state k comma nk parallel. And then for the parallel space, we should be able to find, we're going to try to work with pk v hat acting on k comma nk. So pk, I can rewrite the v hat as h minus h0. When h acts on k comma nk, it's going to give me ek. When h0 acts on that, because I can act the h0 to the left and have it hit the pk, it's going to give me ek0. And that means that that's going to just be a number. So it is going to actually project onto k comma nk perpendicular. The energy that I get is ek minus ek0. That's what we call delta ek comma nk. So what we find is pkv acting on k comma nk will give me delta ek comma nk times the ket k comma nk parallel. Okay? So now let's go ahead and do that. We're going to multiply the pkv times our state, which is this term with the big operators and the inverse. We can also add a pk on the left-hand side of that ugly big operator, because pk projecting onto the state that's already in the parallel subspace just gives the same space, because the state k comma nk parallel is already in the parallel subspace. And that whole thing has to equal delta ek comma nk k comma nk parallel. Now what you can see is, and I'm going to actually put it in a box, so let me move this up just a little bit so we can get to the full box. so that you can see exactly what we're doing here. In the box, we have this operator equation. It's an eigenvalue equation. We have operator. The operator is pkv, quantity 1 minus qk over ek0 minus h0, v minus delta ek, comma nk, whole thing inverse pk, that's the operator, minus delta ek, comma nk. That whole thing acting on the state k, comma nk parallel is equal to 0. So we can call that operator L hat k, comma nk, and then the equation is L hat k, comma nk minus delta E k, comma nk acting on k, comma nk parallel is equal to 0. And that's if you like, that's an eigenvalue-eigenvector relationship, okay? That means that we should think of expressing this operator, Lk, comma nk, as a matrix in the degenerate subspace. So we'll think about taking matrix elements of that operator with each of the basis vectors in the degenerate subspace. It'll be a d of k by d of k matrix. And then we just have to diagonalize that matrix, and we will find the states that correspond to the parallel component. All right? So the way that we really quantify this and figure out exactly what the expansion is, just like before, we're going to rewrite our terms in terms of an expansion in powers of v. So we're going to have a delta ek, comma nk, that's ek minus ek0. So that's a ek, comma nk of 1 plus a ek, comma nk of 2 plus a ek, comma nk of 3, and so on. Each of those superscripts is telling me the powers of v that are in the expression. And then I can also write that operator Lk, comma nk is Lk, comma nk of 1 plus Lk, comma nk of 2, and so forth. And what we're going to be doing is we're going to be restricting ourselves to like powers for the L and for the ek, and that will become the equations that we're going to solve to be able to determine the perturbation of the states and of the energies. All right, in addition, of course, we have to take the parallel state and write it as k, comma nk parallel of 1 plus k, comma nk parallel of 2, and so forth. The convention is to start from 1 here, even though you might say, well, look, there's a parallel component in that 0 subspace, but the point is we don't actually know what it is until we put in at least one power of the perturbation, which will tell us what direction those different parallel states are going in. All right, so for lowest order, delta ek, comma nk will be ek, comma nk of 1. Lk, comma nk will equal Lk, comma nk of 1, which is just pk v pk. Let's go back to that equation and take a quick look at it. You can see that I have a v on the left-hand side there, and that means that that big expression with the 1 minus qk, etc., inverse, I just approximate that by a 1, and I just get pk v pk. Okay, so that Lk of 1 is pk v pk, and we now have this eigenvalue equation. Lk of 1 minus ek, comma nk of 1 is equal to k, comma nk parallel of 1. This is a Schrodinger-like equation. It's an eigenvalue-eigenvector equation. It's a finite matrix, d by d matrix eigenvalue equation that we need to solve. And as I said, what we're going to do is we're going to work out what the matrix is using this basis k, comma nk sub 0, those set of d of k ket vectors. So I'm going to multiply on the left and on the right. I'm essentially multiplying the equation on the left by a k, comma nk prime, and I'm introducing a completeness sum inside the degenerate subspace, a k, comma nk double prime 0 ket producted with a 0 k, comma nk double prime bra. We're going to stick that inside. That's a unit operator inside the degenerate subspace. The p operators are going to go away because everything is inside the degenerate subspace, and that's going to equal ek nk of 1 times the coefficient 0 k, comma nk prime, k, comma nk parallel, because the k, comma nk prime was multiplied from the right on both the left-hand side and the right-hand side. And of course, this now has the form of a matrix times a vector is equal to a number times a vector. That is a matrix eigenvalue-eigenvector relationship. This is also now a matrix equation for the first order energy shift and for the parallel directions that we're going to have to go in. Now, this is essentially all of the formalism that we're going to be working on here, but let's now take a moment to take a look at the simplest possible example of this, which is the case where the degenerate subspace is a 2 by 2 matrix, so the degenerate subspace is two-dimensional. So our H0 is going to be A00A. Those two diagonal elements have to be the same because it's a diagonal matrix, so its energy eigenvalues are both A, and they have to be degenerate in order to have degenerate perturbation theory. Our V we're going to just assume is a full matrix of V11, V12, V21, V22. Because the Hamiltonian must be Hermitian, we know that V12 must equal V21 complex conjugate. So the first order matrix equation becomes the determinant of V minus E of 1 multiplied by the identity operator is equal to 0. So we go ahead and just plug in what that is. We'll get determinant of V minus E of 1, V12, V21, V22 minus E of 1. That whole thing equals 0. Determinant is easy to calculate. I take the product of the diagonal elements minus the product of the off-diagonal elements. I'll get a E of 1 squared minus V11 plus V22 E of 1 plus V11 V22 minus V12 V21. And that whole thing is then equal to 0. Quadratic equation then tells us what the roots are. We'll get a E of 1 is equal to V11 plus V22 over 2 plus or minus 1/2 the square root of V11 plus V22 squared minus 4 V11 V22 plus 4 V12 V21. Okay, now the minus 4 V11 V22, I can bring that into that square root and make it V11 minus V22 plus 4 V12 V21. You can see that will always have real roots, of course, because the energy eigenvalue needs to always be a real number. That's comforting that that will always give us real roots. Okay, so that's what we get for the different solutions of the problem. Now, you're going to find the directions for this 2x2 case by finding the eigenvectors. That's something you're going to do on the homework. It is a lengthy French cooking exercise, so be forewarned about that. That's an exercise that will take you some time to go through. All right, so now let's assume that that first order perturbation theory actually lifts all of the degeneracies. So that square root is non-zero. If that occurs, then EK NK of 1 does not equal EK NK prime of 1 for all NK NK prime. We're now back to the full case where D of K is some number that is 2 or larger. And that means the eigenvalue equation for LK of 1, that is PKV PK acting on the KNK parallel of 1 is equal to EK NK of 1, KNK parallel of 1. That has all of these EK NK of 1s different. That's what it means to say that the degeneracy has been lifted. Now, if we look at second order, what we find is our LK is written now as LK of 1 plus LK of 2. That equals PKV PK, plus we now have to get that first term in that expansion. PKV QK over EK0 minus H0, V minus delta EK comma NK of 1 times PK. Again, we can ignore that constant term when it acts against the state because QK PK is equal to 0. So we can drop that last term and we'll get PK VK plus PKV QK over EK0 minus H0 VPK. And the second order equation becomes PKV PK minus EK NK of 1 multiplied by K NK of 1 parallel plus PKV PK minus EK NK of 1 times K NK of 2 parallel is equal to PKV QK over EK0 minus H0 VPK minus EK NK of 2 multiplying K NK parallel of 1, and that whole thing is equal to 0. We're going to multiply by the vector K NK prime 1 parallel. That's one of the eigenvectors that we found in the first order calculation. We're going to be multiplying by that vector from the left-hand side. I'm not going to read out that whole equation because I'm going to just be saying KNK prime, KKK, blah, blah, blah. It's going to get kind of confusing. So take a moment to carefully look at that equation and see what it is that we're getting. Now, you remember that when the operator PKV acts on this state, it's going to give EK comma NK of 1. So that first term in that line is actually equal to 0. It will also annihilate by acting, it will almost annihilate by acting to the left-hand side in the second term because the PKV PK, that state K comma NK prime, is an state of pk v pk, but its eigenvalue is now ek nk prime of 1, and ek nk prime of 1 does not equal ek nk of 1. So that will give a number ek nk prime of 1 minus ek nk of 1, multiplying the state k comma nk parallel of 2, but it's just a number now. And then with the last piece, we have this operator we've got to calculate. It's a non-trivial operator, and then we have the energy eigenvalue that we're trying to find. Okay? So this is just summarizing again what it is that we're having. We're going to make sure that those first sets of eigenstates are forming an orthonormal basis. If all of the degeneracy is lifted, that's guaranteed that they'll form an orthonormal basis because we are going to normalize those states. And then, as we said, the state pk v pk acting on k nk parallel of 1 just gives me ek nk of 1, k nk parallel of 1. So as I said, that first term disappears. The second term is just a number times that state after we've multiplied it by this other state. So that is a coefficient for the k nk piece inside the parallel subspace, because that set of vectors k nk prime of 1 parallel forms a basis for the degenerate subspace. And then we have this other operator term that we have to try to work on. And of course, because the states k and k are perpendicular, that ek nk of 2 has a delta nk prime that multiplies it. Okay, so to find ek nk of 2, we simply set nk prime equals nk, and then we can just read off from that equation that ek nk of 2 is equal to the matrix element bra k nk parallel of, that should be of 1, I believe. It says 0, but I'm pretty sure that should be of 1. K nk parallel of 1, multiplying by the operator pkv qk over ek0 minus h0 vpk, k nk parallel of 1. Now, that is the same as the non-degenerate second-order perturbation theory if we consider it as a non-degenerate perturbation theory using the basis that we found at first order. So what this tells us is once the degeneracy has been lifted, all the subsequent perturbation theory expansion will look exactly like the non-degenerate perturbation theory formulas. So life becomes very easy once the degeneracy is lifted. It is actually quite complicated, and there are many, many different possibilities that can occur if the degeneracy is not lifted at a given order, or if the degeneracy is only partially lifted at a given order, because then we have to keep working to find how do we determine the parallel directions in that degenerate subspace for situations where we haven't determined it yet. And that does get complicated and technical, and we're going to have lots of examples in the homework to go through that. All right, so we're now going to end with the final part of the summary. In order to get k nk parallel of 2, what we need to do is we need to look at nk prime does not equal nk. I'm not going to do that for you here, but the homework is going to give us some examples for how to go through that. And you can find that because you're getting those different coefficients of the vector k nk parallel of 2, you're going to see it's going to just involve an equation that will help you determine what each of those different numbers are in the expansion for that piece of the parallel subspace vector. And then to get the full vector, of course, once we have the parallel subspace vector, we still have to act that operator on it to give us the full k comma nk. And then also, finally, we have to renormalize the thing at the end to make sure that it's a unit norm state. So there's a lot of things going on, a lot of stuff that you have to remember, but it is, again, fairly straightforward. It's just that there are lots of new twists and turns that you get in the degenerate case, and you really can only see and understand those if you take the time to carefully go through the homework and look at different examples which are showing you different kinds of things that can occur. And it is very, very rich. So there's a lot of different things that we're going to be exploring with degenerate perturbation theory. I think we're going to have a problem on it in our homework for maybe the next 3 or 4 weeks, because there's so many different things that can come up with the degenerate perturbation theory. All right, that takes us now to the end of Lecture 16. Our next lecture, Lecture 17, is going to be looking at some examples of degenerate perturbation theory that come up in determining the atomic fine structure for hydrogen. It's actually a very interesting result that comes up there because it's related to relativistic quantum mechanics, and it's also related to really neat discoveries that led to what's called the Lamb shift, and that then subsequently led to the development of the quantum electrodynamics, the quantum field theory that describes light. And so there's a lot of interesting stuff, a lot of historical stuff in the next lecture that we're going to be going through. And that's all that we have for Lecture 16.